What's up, brilliant brainiacs? Hello and welcome to another episode of SIP Zoyus, S-I-P Zoyus. Today our topic is going to be the Fitness Gram Pacer test, a multi-stage aerobic capacity test that progressively gets more difficult as it continues. The 20-meter pacer test, I'm just messing with you guys. I am trolling you. Hello and welcome. We are going to talk about math, but obviously that's not our subject. We're going to have one subject that we're going to talk about today, and it's going to be graphing factored quadratics. Now, realize in this there's many skills that we're going to be working on. This is a multi-component skill, or not even a skill, but multi-component problem. It's a multi-component topic. It's like an accumulation of everything we've worked on. So, what does that mean for you? That means only 2 examples. So, to all those people who complain and give me flack for having these videos be too long, well, guess what? They're gonna be short because we have only 2 examples. But as we see, they're gonna be 2 juicy examples, 2 very meaty examples, several layers to them, exercising all those math skills and tying them all back into one central problem. Graphing factored quadratics. So, let's go. Graphing factored quadratics combines a whole host of skills to ultimately create a graphical representation of a quadratic function. Okay, a graphical representation. Come on, like let's be real. Let's break that down into real terms. That's just a graph, a graphical representation. It's a image of our graph. It's what the graph looks like. Okay, so we're going to be combining many of these skills together, a bunch of little skills, to create a graph. We're going to graph a quadratic, and we're going to tap into all these skills we've kind of been working on. So let's go ahead. The skills in this are as follows. So here are the skills that we're going to be invoking with it. Factoring, finding solutions, finding x-intercepts, finding y-intercepts, finding concavity, and finding the vertex. Holy smokes, right? A lot of layers to it. Really healthy math problem. Okay, so let's go ahead and go into this, but before we do so, we're going to go ahead and just kind of break down, do like a mini review of each topic, and just some of the key ideas for it. Okay, we're going to go ahead and look at this. So first off, factoring, right? We're going to be factoring these things. They're not going to come pre-factored. That'd be really nice, right? That would be really nice. There's a lot of things in life that would be really nice, right? That we wish would come to us. Maybe like our ex-girlfriend. It'd be nice if she came back, and it would be nice if we got problems pre-factored, but we know that she's never coming back, and when we take the ACT, she's still not coming. I mean, we're still not getting factored we have to do our own factoring on these questions, okay? So we're going to have to do these factoring questions on our own. And so what are some of our factoring methods, right? Well, our primary one, this is our bread and butter, but it's not made of any bread and butter because it's pure fantasy, right? It's magic. The magic method, right? Oh my god. Embarrassing moments on SIP Zoyus. Magig. That's it. Remember the Magig method. Okay. Magic. My bad. We are a few minutes in. We already have a typo. Leave it to Mr. Zoyus. Right? But take that as a great sign. You don't have to be perfect to be good at math. Look at me, right? I did it. And I can't even spell magic. I went to college. Okay. Right? Our bread and butter is going to be magic, the magical method. Right? This is what we're going to do all the time. When we're not sure what to go to, magic method's going to be the main guy. What do we have after this? Well, we have our subtopics, our kind of like special cases. We're going to have our perfect squares. And I'm just going to draw a little square right there, right? A perfect square. And then we're also going to have, actually, you know, I don't like that. I'm going to write a perfect square, but then also write square underneath. Okay, our perfect square, and we got a little square right next to it. And the difference of perfect squares. Okay? So, right? And these are our two special cases. If we recognize that format, we can go ahead and take the shortcut that's associated with it. Okay? Remember the equations that are associated with this, right? Our perfect square is going to be something like this. It's going to be a plus b quantity squared. Right? And that's going to equal a squared plus 2ab plus b squared. Okay, and our difference of perfect squares, oof, going outside the boxes already. Poor planning. Poor planning for Mr. Zoyas, but again, who is surprised? Then we're going to have a squared minus b squared for our difference of perfect squares, right? The perfect squares, there's a difference, and this is going to be equal to a plus b times a minus b. Right? That's the format for both of them. The factored form of each, the expanded form of each. Okay? So factoring, right? Those are our three things. Finding solutions, right? If someone tells us to find the solution, what does it mean? Right? The solution is when y equals 0. Okay? Someone says find the solution, and it's of a single equation, right? Not a system of equations. Remember, the solution to a system of equations is where all the equations intersect. But the solution to an equation, a single one, is where it crosses the x-axis. It's where y equals 0, and we can refer to these as the zeros, the x-intercepts, the roots, and also our solutions, right? But we already know that. That's in the name, so that kind of makes sense. That's expected. Okay, now the x-intercept. So we want to think about this, right? What is the x-intercept? What is the condition of the x-intercept? And for some of you clever cats out there, you're just looking at the video thinking, Mr. Zoyas, wake up, you just wrote x-intercept right there. Right? The x-intercept is this. The solution's the same thing as the x-intercept. Right? They are the same thing. So what's y going to equal at the x-intercept? Y is just going to equal 0. Okay? But also understand specifically, at our x-intercept, we're going to have a point. And this point is going to have this kind of a format. We're going to have an x value. We'll call that a. And what is a? I don't know. It's a variable. It's taking the place of whatever that x is. It could be anything. It could be pi. It could be -2. It could be 1,156. Right? Some number. And a is going to be our x-intercept. And what's going to be our y value? Hint, hint, wink, wink. It's going to be 0. Okay? Cool. Our y-intercept, alright? And so let's go ahead and let's frame what our y-intercept is going to be based on this. Right? What can we say about our y-intercept? Well, what do we know when we have a y-intercept? So we know that if it's a y-intercept, that means it's got to be crossing the y-axis. Okay, so let's go ahead and think about this. We can even look at it down here. If it's crossing the y-axis, let's say maybe right there, what's the x value of that? That's 0, right? What if I pick a different y-intercept? What's the x value of that? It's 0, right? If I pick another y-intercept, what's the x value of that? You might be getting the point. The x value of any y-intercept is going to be 0. So x equals 0 at the y-intercept, meaning that our point's going to have this kind of a format. X, what's x? It's going to be 0. And then b for our y-intercept. This is what our y-intercept is equal to, the b right there. Okay? Understand, this a and b are in no way associated to our standard form. These are generic variables used to represent our x and y-intercept. Okay? X-intercept, y-intercept. Concavity. Okay, so now we want to think back to our form. So what is the concavity? Well, the concavity is our equation, or a quadratic, whether it's opening upwards or whether it's opening downwards, right? If it's opening upwards, what do we call that? Right? Concave up. Upwards concavity. If it's opening downwards, what do we call that? We call that downward concavity or concave down. Okay? So, how are we going to know when it's concave up, when it's concave down? We're always going to look to the multiplier. If it's a positive multiplier, meaning that we have a positive multiplier on whatever our square term is, then it's going to be concave up. If we have a negative multiplier on whatever our x term is, or whatever our square term is, it's going to be concave down. Okay? So understand, oftentimes this means looking at the coefficient on our square. Well, I mean, that's exactly what it means, right? So if it's in vertex form, we want to look at the variable in front of our square term. If it's standard form, we want to look at the first term on our x squared term. That term is always going to tell us about our concavity. Okay, now let's go ahead and talk about the vertex. So for this, we're going to integrate some technology into this. We're going to figure out how to use our calculators to find the vertex. So the vertex, we're going to use our calculator. We're going to use our calculator operations, and we're going to use the min or max feature. Why would we do that? Min or max, what's that short for? Minimum or maximum. And what's our vertex, right? What's some of the things we call our vertex? It's the extrema. It's the turning point. It's the place where we go as far as we can go. It could be the minimum, or it could be the maximum. Right? It just depends. What does it depend on? Depends on the concavity. Okay? Right, so these are all of our topics. That's like a brief overview of what we need to know as we attack these, as we graph our factored quadratics. Okay? So let's go ahead and dig into it. Let's dig into it. Let's go. Okay. This is the equation that we want to graph. Y equals negative 2 times x squared plus 5x plus 3. So let's go ahead and graph it. So let's start off, and if you want, we can go just right down this order. That works. Okay? Do we have to go in any particular order? Kind of, but not really. So you may want to factor it before you find your solutions. You're going to see why. But aside from that, can you do other ones in different orders? Find out different things in different orders? Absolutely. Absolutely. But I'm going to go ahead and go from left to right. Okay? So we're going to start off, and we are going to factor. Okay? Factoring, what am I doing? I'm going to be doing the magic method. Okay? So like a very good mathematician, like a very good pupil, I'm going to go ahead and set up my magic method over here. Oh my gosh, I just spelled McGig again. What is wrong with me? Okay, so McGig. Magic. Right? Multiply, add, group, in common. So, let's kick it off. Right? So just to remind myself, I'm going to write my standard form above my equation over here. So I know what's my A, what's my B, and what's my C. Now I want to multiply. What do I want to multiply? A times C. I want to multiply A times C. That's the first step. So what is my A? Well, I look. My A is a negative 2. And then I look for my C. Right, what was my C? My C is 3. So negative 2 times 3. What's that equal to? That's equal to negative 6. Alright? Now, A. So what does A stand for? A stands for add, and I want to add to values of B. So B is going to be equal to 5. So the game begins. Let the games begin. Best of luck. Negative 6. Factors of negative 6 that add to 5. Okay, so factors of negative 6, what could they be? We're not going to spend all day on this. right? I've done this a bunch, I can recognize it. I'm going to go ahead and try out 6 and -1. So 6 times -1, well indeed that is -6. 6 minus 1, 6 plus -1 is equal to 5. So 6 minus 1 is what I want to go ahead and break this bad boy into. Which term, right? Which term am I going to break apart? My middle term, right? Remember, this is the one I want to break up according to my A step. So we're going to go ahead and we're going to rewrite this equation, except with this middle term, with this linear term, right? X to the power of 1, linear term, broken up. 6x, right? Getting my 6 from there, minus 1x, or just minus x. Okay? Why do we do this, you ask? Why do we break it up like this? It's magic, bro. It's magic. I wish I had a good explanation for it. There's some kind of relationship that we find when we look for factors of this that add to this that just tells us exactly what to separate it into. Okay? But even better question, why did I include the x there? Well, let's go ahead and think about that. We're not changing this term at all. Right? We're not changing what it actually is. We're just changing the way we think about it. We want to think about 5x as 6x minus x. Right? And if we just wrote 6 minus 1, would that equal 5x? Not at all, right? That would be 6 minus 1 equaling 5x. Those are different terms. They just couldn't be equal to each other. That's why we have to include the x. Okay? So now, I'm going to go to my next step, and just being very clean for you guys, I'm going to go ahead and shower. Get it? Being clean for you guys. No. Being clean for you guys, I'm going to rewrite this before putting the group around here. You know, really, I think that's the worst part about these videos is the puns. If you can make it past the puns, you're complaining about the wrong thing. It's not the time that's the problem, it's the puns that are the problem. Why don't I get any suggestions about those? Side note, ooh, what if maybe you submit your puns and then we can have them be a part of the video, or I can somehow squeeze them in. That would be really fun. Yeah, give me puns and it'll be my challenge to get it in the video somehow. Okay, we group this, back on topic, we group this, right? We do the G step, we group it, and now we're looking for in common factors, right? That's IC. Mr. Zoyas does know how to spell, I promise. We're looking for in common factors. Okay, so what's my in common factor here? Well, I have a negative 2x squared, and I have a 6x. Well, I have a factor of x in there that I can pull out. And I also have a factor of 2, right? 2 can be multiplied to 2, and it can also be multiplied to 6. So I'm going to pull out a 2, and now, just to kind of help me a little bit, I'm also going to pull out this negative. Okay, and some of you might be saying, well, there's no negative over here. How can you pull out a negative from here if there's no negative over here? Think about it like this. It's okay to divide this side by a negative, and really that's what we're doing when we factor. We just divide all of it by this term out here, this negative 2x, and then write what remains. But you can also think of a positive as consisting of 2 negatives, right? 2 negatives make a positive. So this, in a way, we can think of as 2 negatives. So it has a negative to spare, so we take one of the negatives out, and we're left with x. We took out one of the negatives from here, and we're left with one negative, which is minus, and then negative 2x, or 6x divided by negative 2x. That's going to leave us with negative 3. Okay? Plus, what can we factor out of here? We have a negative x and a positive 3. What can we factor out? Not much. Not many in common factors, but let's go ahead and also take out this negative. So applying that same reasoning from a little bit earlier, we're going to factor out the negative from the x, and realize that just turns this 3 into a negative. Imagine dividing both of them by a negative. Okay? And if anything, it's like we factor out a negative 1. We factored out a negative 1 from that. Okay? Alright, let's go, let's go, let's go. We did the factoring. Good job. Now we want to find solutions. Okay, so we're looking for solutions. What's the key to finding a solution? Y is equal to 0, right? Y is equal to 0 when we're finding the solutions. So we're going to set all this equal to 0. Oh my gosh, what am I doing? Sorry. I haven't finished factoring. Gosh, I'm getting ahead of myself. My bad, guys. Let's go ahead. We're going to finish the last step of factoring. Pull out our in common factor right here. The x minus 3 and the x minus 3. Okay, in common factor because they're both being multiplied in here, right? This x minus 3 is multiplying the 2x. This x minus 3 is multiplying the negative 1. And then what's left behind, right? We pulled out our negative 3x, so what's left behind? Well, our 2x, right? Our 2x is left behind, right? We cover it up, it's gone. We're left with negative 2x. And what about this term? We cover up 3x, or the x minus 3, and we're left with a negative 1. Okay? And that's what we have, right? And that would equal y. But now, kind of going back, right? So this would normally equal y. I would just write y right there. And so y equals all this stuff. Now it's all factored out, right? Girlfriend came back. We factored it. We had to work for her. But we factored it. She came back. Got our factored expression. Now let's go ahead and write this equal to 0 because we're finding the solution. The solution is when y equals 0. So now we plug in our 0 for where y was. Cool. Now we need to do a little bit more work. We'll do a little bit more math, and we need to say what's going to make this equal 0. Right? Remember, when we're finding the solutions, when they're factored and we're finding the solutions, the key about this is if we get one of these bad boys to go to 0, what's that going to do to everything else? Right? Imagine this goes to 0. We have 0 here. 0 times this. Well, does it even matter what this is? What's 0 times this? It's going to be 0. 0 times anything is 0. So 0 times this is going to go to 0, which equals 0. We're good to go. So we want to find what makes each of these 0. So let's go ahead. We can first just look at this so we can tell that this is going to equal 0 for this. Right? So x can equal 3. But now what about this? What would bring this to 0? And for some of you guys, you may already know, right? You may already know what it is. You may have that math ability to look at it and just see what x should be. But if you don't, that's okay. We can go ahead and make a logical statement. We can say that the stuff inside of there, negative 2x minus 1 equals 0. Right? We can say that because we know that's what it should be. We know all that stuff has to equal 0, so we're looking for an x that's going to make all of it 0. Now we have an equation which we can easily solve. Adding 1 to both sides, 1 equals negative 2x divided by negative 2 divided by negative 2. We have negative 1/2 equals x. Solutions are right here. Okay? Cool. So we found our solutions. Now let's go ahead. We have a piece that we can start graphing, right? We want to think about this. We have a piece that we can start graphing. How can we graph this? Well, remember, the solutions are just the x-intercept. So we can go ahead and take these and graph these x-intercepts, right? It's a solution. It's an x-intercept. They're synonymous. They're the same thing. We can go ahead and put those marks on our graph. It's going to help us start getting a feel for what this guy is going to look like. Or girl. Right? We embrace gender equality here. This could be a female equation. We don't know yet. We actually may never know. What am I saying? I say the weirdest things on here. Okay. So, here are our dots. Okay? Right? We got them from here. Our x-intercepts are solutions. Now let's go back and find our y-intercept. This is going to help give us another point on our graph, looking for our y-intercept. And the y-intercept is going to be a key point. It's a good point to include in your graph. And I'm going to want you guys to start including this in your graphs from here on out. So we want to look for our y-intercept. There's one of two ways we can do this, right? So what's our y-intercept? What's the condition for it? It's when x equals 0. So we're just going to take 0 and plug it in for x, and then see what y equals, right? We have a function. Let's just go ahead and plug it in and see what we get. So our y-intercept, right, doing my work for my y-intercept over here, y equals, and I'll take my factored expression, negative 2x minus 1 times x minus 3. We'll plug in 0 for that. We have negative 2 times 0 minus 1 times 0 minus 3. That'll be negative 3 multiplied by negative 2 times 0 minus 1 multiplied by negative 1. Negative 1 times 3 is going to be 3. That's my y-intercept. I can go ahead and plot that. Right? Y is equal to 3 when x is 0, so we go over 0, up 3. That's our y-intercept. And look, right? You can start connecting these dots maybe. Right? We're going to have some kind of an arc like this. Right? You can see the parabola starting to form. So we're going to have y equals 3. Now, realize I actually just kind of took a little bit of the longer way. There's a shorter way of finding this y-intercept. I want you to go back to here and think about this, right? We took the factored form of this equation. What could we have done instead? Right? What could we have done instead? We could have taken this form. We could have taken 0 and plugged it in right here. We take 0 and plug it in right there. I mean, like, look at this, right? So this is, so imagine if we just took 0 and plugged it into this equation, right, separating it with a dot, 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 we would have y equals negative 2x squared plus 5x plus 3. If we plug in 0 to that, let's think about this. We have 0 right here, 0 squared, times negative 2, plus 5 times 0, plus 3. What's negative 2 times 0 squared? That's 0. What's 5 times 0? That's 0. Both of these go to 0. What are we left with? 3. Which agrees with our first answer. It agrees that this is our y-intercept, which is good. It's always good to have agreement, right? That's the idea of logic. Okay? But so in this, and so let's take a second, let's take a larger step back and look at this. What does this mean? Right? We had our standard form of our equation. Not our factored form, but our standard form. Turned out it was easier to plug this into it. Why? Because we had x equals 0. We plugged in x equals 0, and what happened to these two terms? They went away. They vanished. Kind of like that girlfriend I told you about earlier. Right? They just up and left. I forgot to fold the napkins, and she was gone. And she, sorry, math. Right? Took out these terms, and then what were we left with? Right? We were left with just 3. We were left with just c. Okay? We can look at that. We're just left with just c. So what does that tell us about our standard form equation? This c over here will always be our y-intercept. It's a quick way to read it, right? We see y equals, when we plug in 0 for these are going to go to 0, and then we have 3 left over. Right there. Okay? So it goes to 0, so it gives us a 3 left over. So yeah, we have a lot of these done, right? We factored it, we found our x-intercepts, we did our y-intercepts, and none of these are really new concepts. We're just putting it all together to think about quadratics and to map them, to graph them. Now what about the concavity? So the concavity, there's many ways we can think about this. So we have 3 points on here, right? Now let's think about this. Is there any way I could connect these points so that they're concave up? Right, could I connect these so that they curve upwards? How would I draw a line through these that would go upwards? Right, I would have to like bend it around here. And we know that's not what square functions look like. So what's the only shape it can take? Downwards. Right, something kind of like that. I'm actually not going to draw it yet, just because I want to get my vertex in here before I make my sketch of it. Right, but so realize it's going to be concave down. Now, how can we verify this algebraically? Looking back to our standard form, right? What's our multiplier? Our multiplier is negative 2. Tells us one of two things. First, it's concave down. we have a negative multiplier. Second, we have a stretch of 2. Remember, this tells us the stretch and the concavity. Okay, so it's going to be concave down. Now let's go ahead and find the vertex. And so the vertex, there's many ways to find the vertex, and that's kind of the cool and beautiful thing about it. But we're going to be integrating some technology into here, right? Technologically advanced. Going to get out my calculator, and I'm going to go ahead and enter in my equation. And remember, this is always a great method just to kind of double check that you got the right image, to see that you're on the right path, you're barking up the right tree. So we're going to enter in our equation just right there, and we're going to hit graph. So first things first, wha-bam! Do you see it? Because I see it. Right? It's something like right here. Okay, so this is good. We're on the right track. So now let's go ahead and use this calculator and put it to work. We're putting you to work, sir. No more being on the bench. You're taking up our hours. We're tired of you not working. So we're going to go in here, and how we're going to put this thing to work is with a little function called calc. Secret is, this button can do a whole bunch of stuff. Right? So let's actually go in and take a peek at what it can do. So now we're going to go in with the objective of finding the vertex. But I encourage you to, outside of here, go in and just kind of explore all the functions in here. Right? All these things that are in here. Okay? They all do a specific task, and they're all very helpful. They can all actually verify all of these answers that we have here. We're not going to go into all of them, but take some time to explore these and take some time to figure out what each one does. Quick quiz, right? We see 0. What do we think 0 is going to find for us? Our zeros, right? Our solutions, okay? We're not going to go down that path. We're going to stay on topic. We're going to go for our max or our min. Our max or our min, right? And what's that going to stand for? Our max or our minimum. So which one are we going to have here? Right? We don't want to choose minimum because we don't have a minimum. We have a maximum right there. So we're going to go in, we're going to choose max. Okay? Now it's going to ask us this question. It's going to say left bound. Right? And you may be wondering what bound means. Bound means like to the side of. Bound means going to, oriented towards. Okay, when you think of bound, I want you to think of the movie Homeward Bound. Okay? And that's actually, I think you guys don't know the movie Homeward Bound, but it is a incredible 90s movie, gem of the 90s. Here we go. This is actually what it looks like. This is Homeward Bound, right? And it's all about these animals who get lost, and they're in the forest trying to find their way home, trying to go homeward bound, right? Homeward bound, the incredible journey, and they're making their way home the entire time. Incredibly heart-wrenching movie, I must say, too. There's this part where, oh, poor Shadow. Shadow just, he's not, I'm not going to spoil the movie. Just go watch it. Okay, but bound, right? Bound means going towards. Bound means moving towards. Homeward bound, we are in the direction of. So, left bound, left direction, just means take our cursor and move it to the left of what are we looking for. Move it to the left of what we're looking for. What are we looking for? We're looking for the vertex. So we're going to go ahead and move this to the left of the vertex, right? We know the vertex is right there. So we move our cursor just to the left of it, and then we hit enter, because yes, it is left bound. Now we have another question. Very similar, right? Right bound. So of course we know that bound means on the side of, or going towards. Right, so what is right bound? It just means to the right side of. To the right side of what? Our vertex, because we're looking for our vertex. So we go to our vertex, go a little bit to the right, and then we hit enter. The calculator says guess because it just wants to verify what we're looking for. And how it's going to do that, it's going to show two little arrows above where you clicked. And somewhere in between there should be the point that you're looking for. So then, as long as the point you're looking for is between these two arrows, that means you're good to go. You're going to hit enter on guess. It's going to do some calculations, and we are going to get out our maximum, our vertex, which we are going to see to be 1.25. And some of you may be saying, no, it's not just 1.25, it's 1.25. Ah, I pressed a button. Dang it. Okay, real quick, I'm going to find that again, but you may be seeing all those decimals and thinking, but no, Mr. Zoyas, it's not that. You need to include all the decimals. So realize this is just a calculator. It's going to go ahead and give you all these decimals. That doesn't mean you want to include them. You want the first main numbers. You want the first 3 significant digits, right? That's where your vertex is. You may see 0.999999, that really 0.99999 would just be 1. Right? That's basically 1. That's just a calculator being a little bit of a calculator, not giving you the fully flushed out or simplified answer. Okay, so our x is 1.25 and our y is 6.125, comma 6.125. Just like that. Wha-bam! Using technology to find our vertex, so let's go ahead and we can approximate that. It doesn't have to be exact. But it's going to be over about 1 1/4, about 1.25, and then up 6.125. Right about there. Something like that. That should be our vertex. Now let's go ahead and draw this big, beautiful quadratic. Oh, there she is. It turned out to be a girl. Here you go, Mom and Dad. Here's your beautiful baby quadratic. Oh, look at her. She's so cute. She's got 4 points. And she looks just like that. Okay? Hefty problem. Very full problem. Think about all the skills we're integrating into this. Right? We have factoring. We have solutions. We have our x-intercepts, finding the point and plotting it. Our y-intercepts, finding the point and plotting it. Realizing what concavity is this. And then finding the vertex. We're going to figure out how to do this also without a calculator. But again, calculator, great tool, great to use for it. Okay? Now, real quick, just to include this bit in the video, I'm going to go ahead and talk about how to use our calculator to find our x-intercepts and our y-intercepts. So this is going to be exclusively a technology portion for the video. Of course it's labeled. If you don't want to watch it, skip past it. Don't complain to me about how long the videos are. Skip past the parts you don't need. If you see this in the video and you're like, oh, but Mr. Zoyas, I already know this, skip past it. That's what it's there for. Skip past it. So, without further ado, let's go ahead and go into the x-intercept and the y-intercept using our calculator to go ahead and find these values. So, we are going to go back to this magical section called Calc, right? This is going to have all of our calculator options, all of our graphing options. So we want to go in there and hit second calc. This is going to bring up all of our options. Okay, so we have a few options. So we have value, and what value does is it finds the value of our function for a certain x value. Not a certain y value, but for a certain x value. And how do we know that? We can go ahead and click enter on it, and what does it pull up? It pulls up x equals blank. This means it's going to take an x and plug it into your equation. Okay, so what could we possibly use this for? We can use it when we know what our x is supposed to equal. And we know with our y-intercept that our x is supposed to equal 0. Okay, so we go ahead and put 0 in there, hit enter, bada boom, bada bing, bada boom. Oh gosh, my Italian ancestors are like frowning upon me right now. 0, 3. X equals 0, y equals 3. That indeed is our y-intercept right there. Okay, so we just used the value function in our calc to go ahead and find that y-intercept, right? Value, enter, 3, oops, sorry, not 3, 0, because x equals 0 at the y-intercept, right there. Okay? The other function, now we're going to talk about how to use this to find the x-intercept. So, we're going to go back into that magical calculator place, that magical place that does all our graphing calculations, and we want to look for our x-intercept. Now, do we see x-intercept on here? No. We see intersect, but as close to an intercept as that is, we're not looking for an intersect, because this actually refers to intersecting lines. We don't have intersecting lines. We have a single line intercepting the x-axis, or sorry, the y-axis and we're looking for where it intercepts the x-axis. So we're not going to click that one, but what we're actually going to click, right, the thing that shares the same name as our solution, the thing that is the same as an x-intercept, the thing that's the same as a root, the thing that's the same as a solution, the thing that is a 0. We're going to click 0, go into here. Now, we are brought up of that very emotional movie, Homeward Bound, with our 3 animals, our 3 brave animals that go missing. Chance, Shadow, and Sassy. They go home. They're trying to go homeward bound. They're trying to go home. They are in the homeward direction. So we are going in the left direction. So we want to think about the point we're going to and go bound of it. We want to go left bound of that point, which is our x-intercept. Now, how many x-intercepts do we have? We have 2 of them, right? So we want to be very specific. We want to think about one of these x-intercepts and answer these questions about it. I'm going to start by answering it for this one over here. Okay, so I'm going to go left bound of that x-intercept right there and hit enter. Okay, now same question, right? Reminded of that very emotional movie that came out of the 90s. Golden movie called Homeward Bound. Now we're trying to go right bound. We're going to hit enter. And then we're going to be asked to guess. And remember, the calculator is just saying, hey, do you want me to guess from here to here? And we look and we say, yeah, no, that looks like that's about where our x-intercept is, so go ahead. Calculate that. And what do you know? It calculates it for us. And it tells us that our 0 for right there is negative 0.5 and 0. Which indeed is what we found. Negative 0.5, negative 1/2. Yes, we did it right. Now let's go ahead, let's use this function one more time, but we are going to use this for the other x-intercept. Remember, we have 2 x-intercepts. So we're going to go ahead, go back in second calc, go to the 0. Remember, the 0 is the same as a solution or an x-intercept. Answer these very emotional 90s movie-based questions about being left-bound. Yes, we are left-bound of our x-intercept, which is right there. And then we're going to go right-bound. Our cursor is now right-bound of that x-intercept right there. The calculator wants to guess in between these 2 points. Yeah, that looks good. Let's go ahead and guess that. And whoa! It turns out we were right. X equals 3 and y equals 0. Our other x-intercept. Okay? Just like that. Just like that. Splickety-splat. And we're on to the next problem. Second problem. Holy moly, this video is going on a lot longer than I anticipated. But that's okay, because remember, we got the sections. We got the sections. You can jump from section to section as you need to, or maybe just fast forward to the end and see, did you do the same work as me? It can really be that simple if you want it to. Okay? But going back through this again, let's go ahead. I'm going to work from left to right up here, so I'm going to start just by factoring this, right? I want to graph this. I need points for it. I want to get my x-intercepts or my solutions to this, so let me factor it so I can get out those x-intercepts easily. So I'm going to go ahead and factor this, right, by doing the magic method, because it's our bread and butter, and it's a great method to go to if you are unsure. So we're going to do the magic. We have a times c, right? What is our a? In standard form, this is our a. So our a is equal to 4. Our c is equal to 9. We're going to multiply these guys. So 4 times 9 is going to be equal to 36. And what is b equal to? Well, b is equal to 12. And why did I write b? I wrote b because we are trying to add to b. We're looking for factors of this, factors of a times c, that add to b. That's the name of the game. Let's go ahead and play it. So we have 36. We want factors of 36 that multiply to 12. So what are some factors? I don't know. Let's go ahead and try 6. The other factor would be 6, because 6 times 6 is 36. And what is 6 plus 6? Holy smokes, I got it on the first time. Magic. 6 plus 6. Okay? So we want to use these two numbers to decompose our middle term. This is going to make the magic happen. Every bit of the pun intended. So we have 4x squared decomposing the middle term to 6x plus 6x. Man, my b's look like 6's. They really do. I'm sorry, guys. I need to work on that as a teacher. I'm just breeding confusion with my b's and 6's. Okay, let's go ahead. We'll do the next step. We are going to group this. Plus 6x plus quantity 6x plus 9. We're going to group it right here because of our g, and we're going to factor out the in common factors, which we have here a... Oops, sorry, that's not a 9, that's a 4. That's my bad. I thought I wrote a 4, right? Clarity, very important. I almost just messed myself up there. We're going to go ahead and factor out what we can. Our common factors are a 2 and a x. Dividing this by both terms by 2x, that leaves us behind 2x right here, plus 3. Then plus, what can we factor out of here? We can factor out a 3, leaving us with x plus 3 left behind. Right, 6x divided by 3, sorry, there's going to be a 2 right there. 6x divided by 3 is 2x, 9 divided by 3 is 3. So we get this. We have 2x plus 3, 2x plus 3. Good, that's a common factor. Let's pull it out. 2x plus 3. And then what's left over, right? We take that out, we take that out. And we have 2x plus 3 left over. Holy moly! What do we call that? Call it a perfect square. And for some of you clever cats out there, you may have recognized this, right? How could we have picked up on this and maybe circumvented this process? We could have realized, hey, 4x squared is a perfect square. 9 is also a perfect square. So we could have decomposed that into our perfect square, right? Remember, our perfect square equation's up here. Okay? This is where it's very helpful to have that on tab, to have that memorized and able to be pulled from. Okay? So remember, all of this is equal to y. Okay? So we factored it. Now let's go ahead and find the solutions, right? We factor it to find the solutions because it makes our life easy. So we're going to plug in 0 for y, because remember, that's what we do when we find the solutions. So we're going to have 2x plus 3 squared equal to 0. Okay, now let's go ahead and think about this. If we get this whole term to equal 0, 0 squared, that's just equal to 0, right? So we are going to say 0 equals 2x plus 3. We're going to go ahead and solve this, subtracting 3 from both sides. We have negative 3 equals 2x, dividing by 2 on both sides. And we have negative 3 over 2, negative 3 halves equals x. Okay? Now some of you may be saying, and some of you very, very observant students may be saying, is that our only x? Do we only have one x? I thought we were supposed to have two x's. Where's the other x? And remember, so here's the tip to it. Remember, these are our real solutions. We have one real x right here. And that's okay. Remember, not all of our solutions will be real. And remember, the solutions are just talking about x-intercepts. So could it be possible where our graph touches only one time on the x-axis? Contemplate that question. Contemplate what that would look like, how that would be, and so on and so forth. Okay? We're actually going to find out what that means. So realize that our solution is x equals negative 3 divided by 2. So that's negative 1.5 approximately. So we'll go and plot that x-intercept right about there. Okay. Now we're going to go ahead and we're going to find the y-intercept. Remember, what is the y-intercept equal to? Well, the y-intercept is when x equals 0. And if we plug in 0 to this, right, not doing it here, I'm going to be a little smarter, work a little less hard, we're going to have this term be zeroed out, this term be zeroed out, we'll have a 9 left over. Okay, so writing that out, we're going to have our y-intercept. So y equals 4 times 0 squared plus 12 times 0 plus 9, right? It's going to zero everything out, so our y-intercept is y equals 9. Or remember, we can just realize that in standard form, it's this constant term over here. So that is our y-intercept. It's going to intercept all the way up here at 9. Now the thing about this, right, so let's go ahead and think about this. What shape could it look like? So some of you may be saying, oh, well, it could look like this. It could have downwards concavity. Or some of you may be saying, no, it's upwards concavity. It looks like this. Remember how many solutions we got? We got one real solution, one real x-intercept. At what point can a square function touch a line one time? Not twice, not 0 times. Meaning it doesn't turn around above it, it doesn't turn around and have its vertex before it touches the x-intercept, and it doesn't have our turning point or our vertex after the x-axis. No, it actually has it precisely on the x-axis. Right? When we get this, and you're going to see when we have a perfect square like this, that our vertex lies on the x-axis. It lies right here because it turns around precisely when it touches the x-axis. And we can even turn to our calculator just to verify this and get a better visual of it. Okay, side note, just a heads up, we will have to do portions of this without a calculator. Right, we'll have a calculator for certain portions of it, of these questions when we're quizzed on them, but other portions we will not. So you want to be able to think about this with and without a calculator. So plus 9, we go ahead and enter in our calculation. We're going to graph that. Lo and behold, right? This is what it looks like when our solution comes down, and not right before, not right after, but exactly on our x-intercept, it touches and has its turning point. Touches and has its vertex. Okay? So the thing is, those are all the points from here that we can graph on here. Because let's think about this. Right? If our only x-intercept is right when our equation is on the vertex, what's our vertex? Right? And this is kind of the crazy part. Our vertex happens to be our x-intercept. Our vertex happens to be, negative 1.5, 0. They happen to coincide, and we can even check this out on our calculator going ahead and finding the minimum, right, because we have a minimum here, which, side note, we have a minimum. What's that mean about the concavity? It's concave up. Going and finding the minimum and answering these awkward emotional questions about that 90s movie that is surprisingly sad, surprisingly melodramatic, left bound and then right bound. Yes, I want to guess in between those two arrows. Right? And we have a minimum of negative 1.49999, but realize that's just our calculator getting very close and trying to tell us that no, it's actually negative 1.5. And over here, this is definitely way more confusing, a little bit harder to tell. This says y equals 1.4 e to the negative 11. Okay, just understand, when it's e of a negative number like that, it basically just means really, really tiny. Right? E of a negative number right there means really, 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 really tiny. If you want more of an explanation, look up scientific notation, because that's really what it is. And that's 10, that's 1.4 times 10 to the negative 11. Okay? And if you want to find out what that number is, plug into your calculator. If you don't believe me, it's a very tiny number. So this is just our calculator's way of saying our minimum is negative 1.5 and 0. Because it's so tiny, it's basically just 0. Which indeed is our vertex. Okay? Now go ahead and using our calculator just one more time to find the 0. We're then going to, going back into our calculator using the value the value calculation to find out when x equals 0, aka when we have our y-intercept. Lo and behold, our y-intercept is at 9. Bada bing, bada boom, and again, I did already say it, but the concavity is up. Okay? That'll do it. 2 hefty problems. Enjoy.